Since we are considering an integral as being related to an area underneath a curve, there are a few different ways of calculating that area or having good approximations, and collectively we're going to refer to 4 different ways, and they are all in one sense called Riemann sums. And Riemann is just the mathematician who's given credit to this type of process, and sum just reminding you that we're just adding up area of things. Now, a Riemann sum, there in one sense are 4 different kinds of Riemann sums. There's what's called the left rectangle method. There's the right rectangle method. And I'll write it out. And so we could say the left rectangle area or approximation method. And I'm not going to write approximation method out anymore after this. There's the right rectangle method. There is the midpoint rectangle method. And finally, there is the trapezoid method. Right? And all of these collectively are different ways of calculating the Riemann sums. And so each of these methods just describes what shapes we're going to use to approximate the area under a curve, and the left, right, and midpoint describe where we're finding the height of our specific object. So I'm going to show you how all 4 of these methods work using the same curve. And so in our case, we're going to use the curve x squared minus 3 as an example. So the curve whose area we want to approximate is the function x squared minus 3. And we're going to be focusing from x equals 2 to x equals 6. So first let's consider the graph of this. So the graph, just to give us a picture to work with, of x squared minus 3 is a parabola, and at 2 this has a value of 1, and at 6 this will have a value of 33. So this is definitely not technical error, definitely not to scale, but we have a rough sense that our picture looks something like this. So from 2, 1 to 633, and I'm going to use, let's see how many rectangles. This says 8. I don't really want to use 8. I'm going to only use 4 rectangles, or r equals 4, so I'm going to have 4 intervals. And so my first interval will be, since the whole length of my curve from 2 to 6 is 4, if I break this up into 4 intervals, I need intervals of length 1. So 3, 4, and 5. And the y values at each of these points will be, what's that, 3, 6, 4, 13, and 5, 22. So just kind of labeling some things here. And let's start with the left rectangle method. So the left rectangle method just basically means that I'm going to have rectangles, and the left side of the rectangle will touch the curve. And so what I mean by that, I'll draw my rectangles here in red. So here's my first rectangle, it's going from 2, 1 to 3, 1. Right, so it's this kind of shape here. My second rectangle, the left side of the rectangle, will be touching the curve, and so it will go from 3, 6 to 4, 6. My third rectangle will have a height of 13, and my fourth rectangle will have a height of 22. So my left rectangles involve, in this case, finding the area of 4 rectangles, where the left side of each rectangle is what's touching the curve. And so the area under this curve is approximated by this. And notice, since this function is increasing, my approximation is going to be less than the curve, because the left side will always be the low end, in a certain sense, of every rectangle. And so all of my rectangles, conveniently in this case, have an equal width. So since the area of a rectangle is length times width, and the width of every rectangle is 1, then I've got the width of the rectangle, 1, times the height. And so in the first case, that's 1 times 1 plus the width times my new height, which was 6. Then another width of 1 times my new height, which is 13, plus my fourth rectangle, whose width was 1 and whose height is 22. And when I calculate this, the approximation that I get is, right, the area under my curve is 42 square units, and depending on the circumstances, I might need to label that as far as its meaning. But in this case, my approximation for the area under the curve is 42. Notice that since the function is increasing, then the LRAM would be an underestimate, right? I'm missing some information here, right? None of that stuff got added in. Now I'm going to do an RRAM next, or a right rectangle method. And so the difference between, in the RRAM I'll do it in blue, and the RRAM is just, again, making rectangles, but this time the right-hand side of your rectangles is what's touching the curve. So there's my first rectangle, and my second rectangle, and my third rectangle, and my fourth rectangle. Here it's 6. And so hopefully you can see that in this case, since the function is increasing, the RRAM will be an overestimate, because we're going to have a little bit too much area. So my RRAM, which I did in blue, all of the rectangles happen to have a width of 1, so I'll use the distributive property in this case. And it'll be the width times the various heights. So the heights in this case are 6, 13, 22, and 33. And when I calculate the RRAM, we end up with an approximation of 74 square units. Now the midpoint rectangle, I just noticed I spelled rectangle wrong up here, so let me change that, because that's going to bother me now that I finally noticed it. The midpoint rectangle just means that we're taking the height at the midpoint between the left and the right side. So this one I'll do in green. So if I draw my rectangle, I'm going to have a rectangle. In the middle of my rectangle, at 2.5 is where the height will be. So I'll have a little bit of an overestimate on the left-hand side and a little bit of an underestimate on the right-hand side, and that's going to really balance each other out. So there's my first rectangle, my second rectangle at 3.5. So my rectangle will look something like this. My third rectangle, whose height will be found at 4.5. And my fifth rectangle, whose height will be found at 5.5. So again, it's just declaring where I'm finding the height at. So let me calculate what these values will be. And so for my midpoint rectangle approximation, the width of all my rectangles is still 1, And when I calculate the height at 2.5, the height is 3.25. The height at 3.5 is 9.25. At 4.5 is 17.25. And at 5.5 is 27.25. So my approximation for this area is 57 units. And I feel a lot better about that because each of my rectangles had a little bit of overage and a little bit of underage. So it's balanced out. For the final method, the trapezoid method, I'll reset and I'll do the trapezoid method in a different color. And so when I'm using the trapezoid method, I'm just taking the area of various trapezoids. So first let me sketch them in. So my first trapezoid, again, goes from 2 to 3, and it's got a base at 3 and a base at 2. So it's something like that. And my second trapezoid is this one. And my third trapezoid, and my fourth trapezoid. And hopefully you can see that this is going to be a pretty decent approximation. It's hard to tell how if this is actually over or under because my drawing is so rough, but I have a sense of the shape. And the thing I need to remember is the area of a trapezoid, right? And remember that the formula for the area of a trapezoid is the average of the bases times the height, or half the height times the average of the bases. I prefer the average of the bases times the height. And so when I have to do the trapezoid method, I'm just setting this up. So I know that the height of all of my rectangles is 1, or all of my trapezoids is 1, so that'll stay the same. And then that height is going to get distributed to the average of the bases. So in the first case, it'll be 1 plus 6 over 2. In the second case, it'll be 6 plus 13 over 2. In the next case, it'll be 13 plus 22 over 2. And in the final case, it'll be 22 plus 33 over 2. And when I calculate this approximation, I end up with 58 units for my approximation of the area. So what we've done is we've gone over 4 different ways that you could be asked to find a Riemann sum. They all just involve basic geometric shapes, where the left, right, and midpoint rectangle, they're different in terms of where the height of each rectangle is found, how it relates to the curve. And a trapezoid sum is simply just using trapezoids. And in part 2 of this, we'll do a few more examples where you're dealing with interpreting this area with specific context problems.